So continue on the topic on leaching, we will end it on the calculation of the number of stages. So far, what we did with the first three sample problems are we did only use material balance. And of course, the principles of leaching, that way we can answer the requirements of the problems. Okay, so for now, we'll go further into the calculation of the number of stages. So just like the way we did the material balance, we will do the determination of the number of stages here on doing material balance on each of our thickeners, or that equipment that facilitates the washing of our solids, or there's a direct formula to use only in cases wherein it is appropriate or applicable to. So let me proceed to the next slide. So for batch processes, meaning you don't use multi-stage leaching process, the amount of solute remaining with the solid, so this solute that remains in the solid is of course the solute that is present in your slurry. And since it is the final remaining amount of solute in your solid, it should be the solute on this particular batch process. So it doesn't mean that this solute is already your solution. It's only part of the solution that went with your inert solid. So you are just going to get the amount of solute which is part of the solution that went with your solid, which comprises all in all your slurry. So this amount of solute remaining with the solid is equated to 1 over R prime plus 1 raised to N, where this N is the number of washings necessary such that you will only have this remaining amount of solute in your solid when you are to remove the said solid from your batch leaching process. Now, in this formula, you get to see the R prime. So your R prime is the amount of solvent decanted, or the amount of solvent remaining with the insoluble material. Solvent remaining with the insoluble material. So again, if this part here is the solute remaining with the solid, this one, the R prime is the solvent remaining with the insoluble material. So this left side of your equation and this R prime are all referring to the solute and the solvent respectively present in your underflow. Why? Because it's referring to the solute and the solvent with the insoluble material. So the R prime is the solvent in your insoluble material. This part here on the left side of the equation is the amount of solute with the solid that is leaving your batch equipment process. Okay, so we have an easy formula to use for batch processes for leaching in determining the N. So you can do shift solve, or you can take the ln of both sides of this equation. That way you can get the number of washings necessary. That is for batch leaching processes. Now for countercurrent washing, so you have these representations here, the S, the W, the capital W for that matter. You have the L's, capital L, and you have here the small w. So when you take a screenshot later of this, or when you do your study, you make your notes, you have to make that note there that these W's here at the bottom are capital W, and the W on top are small W's. So countercurrent, your wash fluid here, or your washing solvent, is introduced in this side, and the solids that to be washed will be introduced on this side. Okay, let me just... So this is where your feed is. This is where your feed, and this is your washing solvent. So countercurrent. The manner of representation here is very different than the way it's presented in Giancouplis, because I'm using this time Colson. So I'm using the discussion of Colson on the topic of leaching, because the process of determining the unknowns are analytical. Whereas if you look into what is provided in Gen Kuplis, the process is graphical. So I'd like to teach you something that is analytical. So before we go to the sample problems on countercurrent washing or leaching, determining the number of washings or the number of stages, we need to identify first what Coulson represents with these following letters that you can see. So your solvent washings are written on top of our illustration, withdrawn on top of our equipment, and the feed, the same thing with the slurry, the solids are written here at the bottom. Okay, now I think it's in here on this slide what these letters represent. But by the way, Coulson represents the final stage, a small letter n, and a particular stage is small letter h. Though in our solution later, I will refer to that as I because we're so used with representing a particular stage or a particular general component as I. So I will replace this h by small I, whereas this last stage in your washing would still be represented as N. Okay, that way you won't have to worry about a lot of representations in here. Although you really have to get acquainted with what is L, what is small w, what is S, what is big W, what is Y, capital Y, and what is capital X. Although the representation of the capital letter X and Y are the same as that with Gian Kuplis. So you may take a screenshot of this if you want. That way you can easily go back to your screenshot later for ease of understanding the solution. So this is how we write down countercurrent leaching or washing. Now these are the different representations, or this is how the variables in the illustration are defined. So the R in the formula that I will be presenting a while ago could take any of the four ratios. So your R can be computed based on the amount of solvent discharged in the overflow divided by the amount of solvent discharged in the underflow. What does this mean? Solvent in the overflow is the solvent present in together with your wash liquid. Okay, solvent in the underflow is the solvent that went with the slurry in the underflow. So these are all referring to the final amount. So amount of solvent discharged in the overflow, this refers to the solvent present in here. The solvent present in the final washing. Okay, that's the numerator for this particular R. Whereas the amount of solvent discharged in the underflow in the denominator is the solvent present here in the final slurry, removed in the nth thickener. Okay, only the solvent. So take note that it's only referring to the solvent. R could also be solved based on the amount, this time not the solvent, but the solute discharged in the overflow could be the amount of solute discharged in the underflow. So same thing with what we have here on the first ratio for the determination of the R. Only that this time we change the solvent to the solute. So solute ratio in the discharge overflow and underflow. Now, the other one is the amount of solution. So you can use solvent, you can use solute, you can use solution. So when we speak of solution, this already comprise the solute together with the solvent. So that's the solution that we are referring to in leaching. So the amount of solution discharged in the overflow over the amount of solution discharged in the underflow, or that goes with your inert solid in the slurry. Now, the different letters that you see there on the streams, the small w or the omega is the quantity of the solution in the overflow. So these are the quantity of the solution in the overflow. Small w, or that's your omega. The L is the amount of solute in the overflow. L is amount of solute in the overflow. S is the amount of solute in the underflow. And S sub O, since it's using already the subscript O, meaning 0, is the amount of solute in the feed. So solute present in the overflow is represented by L with the appropriate subscript based on that particular stream where your wash liquid is coming from, or particular thickener in which your wash liquid came from, and S is solute in the underflow. So 0 lang siya ang subscript kung sa feed. S sub N naman siya kung sa final slurry removed in your nth thickener, the final thickener. Now, the capital W is the amount of solution in the underflows. So, the amount of solution that went with your inert insoluble solid in your slurry, and they are present in the underflow. You need to affix as well the subscript here based on that particular thickener where this particular underflow lives. And then W sub O, capital W sub O, is the amount of solution in the feed. N, small letter N, is the minimum number of washing, which refers also to the number of thickeners to be used. Now, Giancouples represents X as the concentration of the solute in the overflow, and it's the same with Coulson in here. So X is the mass of solute over the mass of solution in the overflow. Y is the mass of solute over mass of solution in the underflow. So notice that these particular concentrations, so I did not place anymore here X, Y, whether we're referring to X and Y, it's mass of solute over mass of solution only, which is mass of solute plus mass of solvent. In the underflow, wherein you have the presence of the solid, you don't account or you don't add on the mass of the solid here in determining the concentration of the underflow. It's the same, mass of solute over mass of solution, only that it's represented differently. X is for overflow, Y is for underflow. So this is the opposite of the usual way we represent concentrations, wherein basta sa babaw gani nga gas Y, ang sa dalom nga liquid X. So there is a leaching suli sila. Okay? And contrary to the usual way we express concentrations, here we only speak concentration of the solution. We don't account or we don't include the inert insoluble solid. Now, what are the very important assumptions? These assumptions are very important when we do calculations concerning leaching. And we did apply or we revisited some of these assumptions when we did material balance in the last sample problem we did last meeting. So solid concentrations in the overflow and the underflow are always the same. So whatever is the concentration of the overflow solution, that would be the concentration of the underflow solution that went with your slurry. Now, there is perfect mixing. That means at any point in your thickener or in your washer, the concentration of your solution is the same. And this perfect mixing also ensures that you get to remove the maximum amount of solute removable from your inert insoluble solid. Now, the solute is never adsorbed in the solid, so wala siya kakabilin sa babaw sang inert insoluble solid. Now, the amount of solvent removed with the insoluble solid in the underflow is constant. The amount of solvent removed with the insoluble solid in the underflow is constant, and this is independent of the concentration of the solution in the thickener. So this does not depend on the concentration of the solution in the thickener. So meaning what varies here is simply the solute content of your solution, because it says here in number 4, the amount of solvent removed is constant. So it does not depend on the concentration of the solution. So meaning, even though the concentration of the solution varies, this is due or this could be attributed to the change in the amount of the solute, but not that your solvent is changing in the underflow. So number 5, the amount of solvent leaving each thickener in the underflow will then be the same. So related to this. So solvent leaving each thickener will then be the same. The amount of solvent in the overflow are also equal. The amount of solvent in the overflow are also equal. So what changes in the overflow is again the solute, because the solute, if we like to look on it, as the washing proceeds countercurrent fashion, as your solid proceeds in your system, it carries more and more solute. So the amount of the solute increases. But the wash water that does that, the volume or the mass of the wash water that does that, referring to the solvent, is still the same. It's the solute that increases. So it follows that the concentration as well increases. So these are the very important things you need to look into, the assumptions that you need to consider, principles related to leaching, or principles that specifically we need to apply to counter current washing or leaching. You may take a screenshot of this particular page. That way, when we do our computations as well, although I do get back from one particular slide to this, you are acquainted with the different representations. Okay? Now, here on the next are the formulas. So your number of washings or your number of thickeners that will accomplish a certain degree of removal of your solute from your solid will be this. And R can be computed in any of this particular, by the way, it could be computed or it could be taken from the problem itself, because your R here could be any of this. So a problem will give you right away its value, or you need to solve it based on whichever of these three is given to you, or which will make it possible for you to determine the R. So you just substitute the R there, but you still need to determine the F, which is in turn also dependent on the R. So your F is this. And if you have a pure liquid solvent, meaning since most of the time it's just water, but if it's not water, as long as that solvent is pure, it doesn't contain a small portion of your solute, you can solve for the N. You can solve for the number of washings or thickeners based on this ratio. Now, S is the amount of solute in the underflow. So you can use this amount of solute in the underflow ratio with the amount of solute in the feed to get the number of washings after you have determined the R already. Again, choose the appropriate formula for the R based on what is given. Or you can have this particular formula. Again, you get to see the N here, the number of washings here, together with the R. But this time, instead of working on the solute present, you will have now the W, which is the solution in the underflow. So the solution in the feed, solution in the final thickener, W sub N. While this one is the wash liquid introduced in the N thickener. Since this one is written as small w, or omega sub N plus 1. So any of this formula, as long as applicable, could be used in determining the N, the number of washings. Now, if you do material balance on the system as a whole, so system meaning you have several thickeners already, you can do solute and solution balance. So you balance the solution that enters and you balance it together with the solution that leaves your system. So this is the wash water. This is the solution in, okay, I think you cannot see This is the solution in your feed. This is the, no, this is the wash water, okay? The solvent plus the solution in the feed should be equated to the solution present in the final wash water, leaving thickener 1. And this is the solution present in the end thickener in your slurry. So what you're balancing here are all solutions. Now, you can also do solute balance. So solute, this one is the solute in the feed. This one is the solute in the final slurry or the slurry from the end thickener. This is the solute present in your wash water kung may ara lang. Kung wala, wala man. And this is the solute present in your thickener number 1. Okay? So you just do your usual material balance. You can also represent your X1. X1, what is X1? The concentration of the solute that leaves your thickener number 1. If you're going to look at it, that's already the thickened wash water. Why I say it's the thickened wash water? Because it carries already the maximum allowable solute that it can from the solid. Based on the fact that it leaves your thickener number 1. So its concentration will have all the solute. This one is taken from the material balance of the solute. So you do material balance of the solute, and in this case, you're getting L1. So your numerator here actually is L1. Your L1 is L sub n plus 1 plus SO minus S sub n. So actually, it did not be written here, but this is how you determine the concentration of the final wash water. So this numerator is L1, and this denominator, of course, will be your omega 1 or W1. The solution, the total amount of solution leaving your thickener number 1. So that would be omega n plus 1 plus capital W sub O minus W sub n. So this is the concentration of X sub 1. If you are going to be asked what is the Y sub 1, what should it be? If this is X sub 1, the concentration of the overflow, what is your Y sub 1? The concentration of the underflow that leaves thickener 1. You may write on the chat box. This is the concentration of the solution that leaves your thickener number 1, which is your final, shall I say, thickened wash water. It took already the maximum amount of solute it can from your solid. So this is its concentration, solute over solution. We took this one from here. We solved for L1, and we took the denominator solving for small w1 or omega 1. So my question is, if this is the concentration of your solute in the final wash water, removed as product of leaching, what is the concentration of the solute in the underflow slurry for thickener number 1?
The same man, miss.
Correct. So the same ha, the same. Balik-balik, kita ginabalik-balik kung gikay kalipatan na if you're not able to recall that they are equal, you will have difficulty later doing your material balance. Solute concentrations in the overflow and the underflow, referring to the same thickener, are always the same. They are always the same. Okay, where was I? Sorry. Okay, so we have that. If you balance on the first H thickener, or if I may replace this H by, oh, where's my pen? If you're going to change this H here, as I've mentioned a while ago, to I, if you balance on the first I thickeners, meaning not including the final end thickener, so this is how you balance it. Anyway, class, the way you do this one, the principle behind is exactly the same as this, whether you do material balance or you do balance until the H thickener or I thickener only. So this could be solute in the wash liquid that entered your thickener I. So that is why it's L sub I plus 1. The representation here of Coulson more or less is comparable to that of Jean Couplis. Plus the solute in the feed, this one, is equal to the solute from thickener number 1, because it's from thickener 1 to thickener I, and solute in your thickener H that went with your slurry. So these are all solute present. Okay, solution, you do the same. So you can change this one to I. But if you intend to go with the original representation of Coulson, which uses the ayat thickener or represents the ayat thickener as the H thickener, you may do so as long as you properly write that in your drawing or representation. Okay, solute, solution, and then the concentration then, so this is the concentration of the wash water that entered your thickener I. The concentration of the wash water that entered your thickener I, referring now to the wash water I sub 1. So where do we get this? Halin man na di siya gyapon. So in this case, you have L sub I plus 1 minus Sn plus SH. This is SI. So we just change the N here to I. This is also I. Okay? So there's an this question. Would X2 be equal to X1? What you mean, Bobby? Concentration of the wash water leaving thickener 2 equal to the concentration of the wash water leaving thickener 1?
Yes, miss.
No. Hindi kay simple lang samtang naga-proceed na ang wash water mo sa imo, countercurrent watching, it carries with it more and more solute.
Bali, maano lang siya, miss, X sub 1 equals to Y sub 1. X sub 2 is equals to Y sub 2. Amo lang na siya.
Yes.
Okay.
Ang naga-live lang nga mga streams on a particular thickener ang equal ang concentration. Pero ang washings mo yan, hindi gina-equal ang concentration kaya ga-increase ang solute content sina.
Thank you, miss.
Sige. May questions pa? Wala na question? By the way, class, if you're not comfortable with the representation of Coulson, you would like to stick with the representation of Jean Couplis in leaching, it's fine with me as long as you make your representation homogeneous. So kung imo figure, nag-illustrate na using the representation of Jean Couplis of N for solids, concentration, B for the amount of solid, then you do so, okay? You may not use the representation of Coulson, but I suggest so that you will not get confused when you ever applying the formula of Coulson, stick to his representation. Hindi mo na siya pag i-convert sa representation ni Jean Couplis. I don't discuss normally the graphical approach of Jean Couplis in leaching because it does not have an equivalent analytical procedure. So in this particular topic, I really shift to using Coulson because it has the analytical way of determining the number of stages. In the case of Jean Couplis, puro na siya graphical, wala kasang lain niya sa iban nga unit operation process nga ma-compare mo bala, may analytical kaka-graphical, pwede mo maubra kag i-compare ang ilang results. Sa sini nga topic, wala na kay Jean Couplis. So that is why, in case you're wondering why burden you with so many representation, because Coulson discusses the process analytically of the determination of N. And so far, I haven't yet used a different reference. analytical way or analytical procedure of determining the N other than Corson. So maybe in the next years, or maybe you can do that as well. Okay? But for now, you have any questions here before we go to the problem? Sige. So we'll clear my markings. So we go to the problem that we have. So the problem actually has the same questions, but two different scenarios and how you're going to go about finding this particular unknown. So a plant produces 8,640 tons per day, equivalent to 100 kilograms per second of titanium dioxide pigment. This titanium dioxide pigment, which must be 99.9% pure when dried. So after the process of washing for this titanium dioxide pigment, which has some contamination, which I'm going to read in the next statement, removing the contamination does not ensure that all the contaminants are removed for any, let's say, on the real setup. But in this case, we think of it that whatever is left is just removed together with the water. So when this titanium dioxide pigment is washed with water and dried later on, it will contain 99.9% only titanium dioxide. The pigment, titanium dioxide pigment, is produced by precipitation, and the material as prepared will have some degree of contamination, just like in any other processes. And that contamination is in the form of this 1 kilogram of salt solution. So the contaminant for every 100 kilogram per second of titanium dioxide pigment is 1 kilogram per second of salt solution, which has this much of the salt per kilogram of the pigment. So the solution contains the salt and the pigment. Now, the material is washed countercurrently. So the purpose of the washing is, of course, to eliminate this contaminant. Kasi kung wala naman lagi siya contaminant, diretsyo na siya tani sa drying. Kaso ka may contaminant siya, kinalan siya mag-undergo washing. So the material, due to the presence of the contamination, is washed countercurrently with water in a number of thickeners arranged in series. Now you are asked how many thickeners will be required if water is added at a rate of 17,400 tons per day, equivalent to 200 kilograms per second, and the solid discharge from each thickener removes 0.5 kilogram of solvent per kilogram of pigment. So this is the rate of solvent removal in your slurry. The solid discharge from each thickener removes 0.5 kilogram of solvent per kilogram of pigment processed. Now, the same question, what will be the required number of thickeners if the amount of solution removed in association with the pigment this time varies with the concentration of the solution in the thickener as follows. So in the first question here, class, we are to assume that there is no variation in the concentration of the solution based on the amount of solution present in your slurry. So in this first question, how many thickeners, still N, we will assume that there is no variation in the concentration of solution based on its amount present in the slurry. In the second, it's the same question. However, we have to look into this relationship, or we have to look into how the concentration of the solution varies with the amount of solution removed, or vice versa. How the amount of solution removed varies with the concentration of the solution. And you have here the corresponding set units for this degree of variation. Since this one is your concentration of solution, and if you're going to look at it, the set units is kilogram solute per kilogram of solution. And this one is the amount of solution removed, kilogram of solution per kilogram of pigment. We can say later on, when we write our given in the Jamboard, initially we can say that this one is referring to what you have in the, okay, you don't see my pen. This one refers to the amount that we have in the overflow. Concentration of the solution, which is kilogram solute per kilogram of solution. The same concentration of the solution in your overflow is the same concentration of the solution in the underflow for streams leaving the same thickener. So if this is X1, for example, this is X1, which is 0.1, this is also Y1. If this is X2, then this is also Y2. Okay, because we have that primary principle that the concentration of solutions in the overflow and underflow of a particular thickener or washer are equal. So this is referring to either X or Y. For this one, amount of solution removed, you could see that it's expressed in terms of per kilogram pigment, meaning per kilogram of titanium dioxide processed in your thickener, then this must be referring to what you have in your slurry, Gidya. Okay, it is in your slurry. And based on the different letters that Colson is using later on in his material balance, this could be looked into as the W. Specifically, if you have taken a screenshot of those different letters that he used, this refers to the capital W, amount of solution in the underflow or that went with your solid in the underflow. Okay? Now, the final sentence says here that the concentrated wash liquor is mixed with the material fed to the first thickener. So meaning the final wash liquor, so it's your concentrated wash liquor that is referring to your omega-1 or your small W sub 1 is mixed with the material to the first thickener, meaning it is mixed with the feed, the raw feed, which is this 100 kilograms per second of titanium dioxide. And then so on and so forth. The process is done countercurrent. So in the first thickener, what actually is being mixed or what is being used as a washer for your original feed introduced in your system of washers is your concentrated wash liquor. So you have your concentrated wash liquor and then your feed being contacted in your first thickener. Okay? Please take a screenshot of our problem. We'll do the representation, the graphical representation in the Jamboard. Okay, so we'll now go to our Jamboard. Okay, wait, class, ha. Well, stop sharing because I cannot see it. Okay. So here we go. So we'll first draw the original setup. Actually, this is still the setup. However, in the first case, the amount of solution, the amount of solution removed in your slurry is not dependent on the concentration of the solution. So meaning it's constant. While in letter B, still determining N, this time you have the two relationships given to you. So this is your setup. So we'll try to draw it here. The simplest possible way so you can visualize. Let's say this is your dryer. This is thickener 1. This is thickener 2. This is thickener I. Dot, dot, dot. This is thickener N, the last. Okay. This thickener 1 is connected to thickener 2. The reason why I place a dot dot here and I have two sets of arrows here, it's because after thickener 2, there are several still thickeners here before you reach a particular thickener I. This particular thickener I is the thickener H in the representation of Coulson. And from this thickener I, you have this nth thickener, the last thickener. So what enters as wash water or your solvent in the nth thickener is your omega n plus 1. So if you recall, omega n plus 1 or small w n plus 1 is the solution in your overflow, constituting your solute and your solvent. So please check your notes there. So this must be, since this part here actually is omega this is to be interpreted base here to be omega n, which is also your omega I plus 1. Because it enters your ith thickener. So then, based on the representation of Jan Kuplis on a particular stream entering a particular ith stage, you always add 1 to its subscript, meaning plus 1 of that particular stage. This is your omega I. This is your omega 3 coming from this one, from 2. So then it receives omega 3. This is omega 2. And this is omega 1. So these are solutions that I have written. Now, in terms of concentration, you can have capital X1 here or capital Y1, capital X2. They could be interchanged, but you will be confused if I write the X there. So I'll place it Y na lang. So anyway, that's also X. So Y1, we know the underflow is Y. So YI and YN. But that's still same as X. Now we have the feed here. I'll just write the details of the feed here. So your feed is 8,640 tons per day, equivalent to 100 kilogram per second. And then this has contaminant in the amount of 1 kilogram solution. This 1 kilogram solution contains 0.55 kilogram of salt per kilogram of pigment. So that's the purpose of the washing because of this contamination. Now here in the thickeners, you have actually W1 capital, W2, W3, and W4. If I will represent it generally as W for letter A, it says here that your slurry contains 0.5 kilogram solvent. Okay, based on our representation of capital W, 0.5 kilogram solvent per kilogram pigment. Okay. Now, from here, you have your slurry from the end thickener fed to the dryer, and it leaves the dryer containing 9.9% titanium dioxide. Your wash water, this omega N plus 1, I'll just write here, is 17,400 tons per day, equivalent to 200 kilograms per second of wash water. Okay? So far,
Miss, ang W na, miss, amo na siyang sa W sa buwan. Ay,
hindi. Ang W sa buwan tabab, ari di sa
ang American.
amo giniya ang thickened mo nga wash water, gindalayan na ni ang solute. Iniya pure pa ni, wala pa ni dala solute. Okay?
Yes, miss. Thank you, miss.
Sige. What else? If you took a picture of the problem, have we placed everything there? Let me check. I will read it again. It produces 100 kilograms per second. The plant, titanium dioxide pigment, which must be 99.9% pure when dried. The pigment is produced by precipitation and the material as prepared is contaminated with 1 kilogram of salt solution containing 0.55 kilogram of salt per kilogram of pigment. The material is washed concurrently with water in a number of thickeners arranged in series. How many thickeners will be required if water is added at the rate of 200 kilograms per second, and the solid discharge from each thickener removes 0.5 kilogram solvent per kilogram of pigment. So this is your solvent concentrate. This is the amount of solvent removed in your thickener, which is fixed already for the first scenario of finding N. For the next requirement, what is also the required number of thickeners if this time the amount of solution removed in association with the pigment varies with the concentration of the solution in the thickener. So the first one, there's no variation in amount of solution removed based on concentration of solution. So both are asking for the number of thickeners. Okay, so let me go back to our Jamboard. Okay, so this is our Jamboard, and this is for A. Removal of solution is not dependent on solution concentration. Letter B is a different story, so we'll just write B here so we can go back to it later. So you have here the concentration of solution. This can be represented either as X or Y. And this is kilogram solute per kilogram solution. Okay? Concentration of solution. The other one is amount of solution removed. other column. So amount of solution removed, we only remove the solution in the slurry. So amount of solution removed, this is kilogram solution per kilogram pigment. Okay, so we'll have here the different values. So you have 0, 0.1, 0.2, 0.3, 0.4, 0.5. And here you have 0.3, 0.32. So there's an increment, actually a constant increment of 0.02. 0.02. So this must be 6. So we have 6 and 0, 1, 2, 3, 0.38, and 0.4. So that's for letter B. So in both scenarios, we're asked for N. If I go to the problem again, for those who have not taken the screenshot, you may take a screenshot so you can easily follow later. Okay, so this is for B only. This one is for A. Hi. So I'll go back to the Jamboard. Now, next to the slide, next would be the solution. So since in the first scenario, there won't be any variation in the amount of solution removed based on the concentration of such solution, referring to the slurry, then we can have this overall material balance in kilogram per second. And we do it just like what we've done in our third sample problem. We do it in tabular form. So feed from the reactor, we have our wash liquor or our solvent. We have the washed solid. This refers to the final underflow, and the liquid product. Okay. So in here, what do we need to balance? We need to balance the titanium dioxide. So your titanium dioxide class is your solid. This is your solid. Your inert, insoluble solid. Then the salt, identity of which is not known. So we'll just place this as salt. And then you have the water. Now, based on the feed, so if you have taken a picture of the illustration and of the problem, this is our illustration. And the problem which you took a picture a while ago, what is the amount of titanium dioxide in kilograms per second in the feed from the reactor? Okay, that would be 100. Correct. So we'll place here 100. Do we have the salt present on it? What is the amount of salt present on it? Okay, correct. It's 0.55, right? 0.55 per kilogram of pigment. Since the processed pigment is 100 kilograms per second, so Gio, that is correct. It's 55. That's 0.55 times 100. So this
Miss
is...
excuse lang. Ang sa picture, bala miss nga sa problem, gid 200 ang 200 kilogram per second siya, hindi 100.
ang,
As a problem gid itself,
dali
hindi
lang,
siya 100 kilogram.
we'll see. And Bob,
So ang 17,400 tons per day, 200. Ay, sali.
feed. Feed, Bob.
Gali iya.
Okay. Feed, Bob. Ang feed. Din ako to.
Thank you, Miss.
It's okay. What about the water? So the presence of the water in the feed actually is based on the contamination. So what is our water content here? Correct. Correct. Kaya kung 0.55 for every kilo, that would be 0.45 ang water because we only have salt and water in our contaminant. So you multiply it by 100, that would be 45. Okay, so this is 45. Now we go to the wash liquor. Wash liquor. So what is our wash liquor? Does it contain titanium dioxide? Okay, of course, none. Okay, wash liquor siya gani. So there's no titanium dioxide. It doesn't contain salt. Okay, ang salt ara is sa aton feed. It contains only water. So amo na siyang ginahambal mo kay Nabab. The amount is 200 kilogram per second. Now, what about the washed solid? The washed solid. What is the amount of titanium dioxide in the washed solid? Me write on the chat box. Remember that this washed solid is your inert insoluble solid. Where did it came from? From the feed. Yvette, washed solid. Dali lang. Do you understand what is the washed solid? It's the slurry leaving the last thickener, the end thickener. Okay, correct, Gio. Very good. It's also 100. Kaya ang inyo insoluble solid, kung ano ang nagsulod to, mo gina siyang magwa. Okay, sakto na Yvette. 100 gali. Hindi nan ha? Okay, so 100 on the titanium dioxide. What about the salt content in the washed solid? Pila ang salt content sang washed solid? Where will you get this particular answer? We'll go back to the illustration and go back to the picture of the problem so you can answer this one. What is the amount of salt present in the slurry leaving the end thickener? Salt. Look in, okay, sige, here's somebody. Very correct, Nika. Nga 0.1, Nika. Why is it 0.1? You can write it on the chat box. It's 0.1 here. Why? Your wash solid contains 0.1 kilograms salt. Correct. Your dryer, your material, your slurry that was fed to the dryer is only 99.9% pure. So meaning, may nabilin pa nga NaOH on the assumption that all the water was already taken out from it. Nadula na ang tanang nga tubig, dried na siya. So kay 99.9% pure lang sa meaning, pagwa niya sa last thickener, when it leaves your last thickener, it has 0.1 kilogram of salt. What about the water? What's the water content?
None, Miss.
Correct, Jeanette. 50. 50 ang water living with the washed solid. Now, Jeanette, what's your basis in placing here 50? You can write on the chat box. Si Gio bala, charot, 0.5 times 100. Miss Gio, will you explain why you have, where do you get this 0.5 times 100? Where did you base that, Gio? Or I'll go to Jeanette because Jeanette was the one who gave us the 50. Where did you base the 50 kilograms water? Ay, very good, Jeanette. So if you read the, if this is not, if you can read the, what's on the chat box, the thickener, so it's based on the statement for this scenario that the thickeners removes 0.5 kilogram of solvent, the solvent is water, per kilogram of pigment. So if the pigment process is 100 kilograms per second and it removes 0.5 kilograms, then 0.5 times 100. Very good, Jeanette. So that's the reasoning behind your 0.5 times 100 because you're processing 100 kilograms per second of pigment. So you have water in the wash solid. This wash solid is referring to the slurry from, again, I'm emphasizing the slurry from the end thickener. Now we go to the liquid product. This liquid product is referring to the what? What's the other phrase that you can use for the liquid product? And it's just written here as liquid product, kay short sa isulat. So, but it's referring to the wash, to the what? You may write on the chat box, the liquid product is referring to the ala, ang liquid product, you do not know from the term product. The product.
Overflow, miss, sa first ka thickener.
Correct. We say it's the concentrated washed liquor. The concentrated washing liquor or the concentrated liquor, wash liquor. The overflow leaving the first thickener. Okay. How do I, of course, we know that it doesn't have any titanium dioxide here because it's in the form of a solution of your salt and water, right? How do I get the salt and water here? The last two column values for our liquid product. How do I get it? Pareho lang na siya sang sample problem. Number 3, how do we get the row value?
200.
You have to do mass balance. So, anong mass balance na pinakasimple dire? Anong pinaka 200 times? Ano na klase mo 200 times man? What you mean, Bob?
Ay, hindi means hindi sila, miss.
Okay. Pareho sa sample problem number 3. How did we complete the last row of the consisting of the information of the product of bleaching? And that's your liquor, your concentrated wash liquor from the first thickener. We do correct. Correct. So you do mass balance by using the values here that you have. Dire mga values di. So the feed to the reactor is 55 in terms of the salt. The wash solid, that's the solid from the last thickener, contains 0.1. So meaning, di nagkadto ang iban there is a liquid product. So you subtract the two. So this is 54.9. While this one, wash liquor plus 45 feed from the reactor minus 50. This is 195. Okay, you're correct. You do mass balance based on the values that you have here. So I'll place an asterisk here from mass balance. Okay. No questions here? Any more? Sige. We'll continue. We'll go to the next slide. Now, since your solvent is pure, and we have to look for a formula that will help us rather solve for the n, you have this formula presented to you a while ago in the slide. So I'll write it here. We can use this because we're using pure solvent. Okay? Now, in this formula, we don't have the R yet. We still don't have the R. So I'll just have this as equation 1. So as a review, what do we have for the S? S is solute in the underflow. So this is solute in the feed. So this is solute in the feed, SO. Solute in the nth thickener is SN. R, we need to solve. We can find N afterwards when we know already the R. Now, what is R? So we have 3 different formulas for the R that we can use. But this time, we'll have R based on solvent in concentrated wash liquor. Okay. Connection is unstable. And solvent in solution, leaving the nth thickener. This is one of the formulas, the 3 formulas for R. Okay, class? So we will substitute the solvent that we have in our concentrated wash liquor. Kaya na, isa to siya sa assumption that our solvent, okay, you wrote on the chat box, I don't know if sa ako ng Miss, nadula ka, Miss Choppy ka. Oo, okay, unstable ako. Batian nyo na ako, subong. Choppy ka, Miss. Sadya. What about now? I can still see your chat. Can you still hear me? Still choppy? Oh. Wait class ha. Wait lang.
LTE in Shopee only, not Roblox.
Oh.
Okay.
Can you hear that? I'm talking to her, telling her you're doing internet there, so that is why I'm choppy. I'm still choppy. Can we proceed, class? Can you hear me already? Sige. Okay. So your R will be based on the formula solvent in the concentrated wash liquor over solvent present in the solution leaving the nth thickener. So this is one of the 3 formulas. So we'll have this as 200 divided by 50. So where is that coming from? I took it from here. 200 divided by 50. The solvent in the concentrated wash liquor and the solvent on the solution. The solvent in the solution leaving your nth thickener. Okay? So we have here 4. Our answer here is 4. Then we can go back to our equation 1. So from 1, So your S sub n, what do you think is our S sub n? Solute in the n thickener. Solute in the n thickener. This is 0.1, right? So I'll write here 0.1. So that's based on the definition of the S. And solute in the feed, which is 55. Where do you get that, miss? Here. Solute in the feed. The solute. I'll write this one is the solute. Funny. It's the pointer. This is the solute. Okay? So solute in the feed is 55, solute in the washed solid, and that's the slurry from the end thickener. Okay? So we're using these two here. Then we can just substitute. So you have 4 minus 1 divided by 4 raised to n plus 1 minus 1. Now you will tell me that you will shift solve again, but you can solve this analytically. So this is 3.1 divided by 0.55. You transfer it here, so you will have 4 raised to n plus 1 equated to 1,651. You take ln of both sides, you will have n plus 1 times ln of 4 equal to ln of 1651. You can solve for n, and that n is equal to 4.34. So the number of washings or thickeners is 4.34. Oh, choppy naman ko no. Can you hear me, class? Okay, so you can see the solution. Can you follow the solution? So this is the number of thickeners, 4.34. Let me know if you have any questions here. No questions? Just give me a thumbs up sign there so we can proceed. Okay, you only get to see one. Everybody can follow through the solution. Miss nga, 55. Tina Gio. Okay. SGO is solid content. So solid in the solute, not solid. Solute in the underflow. So in here you have solute in the end thickener for your S sub n. This is your solute in the end thickener. Based on our table, that's 0.1. Wash solid contains this amount of solute, 0.1. Now, what about this 55? Solute in the feed. How much solute do you have in the feed? Feed from the reactor contains 55 kilograms salt. So that is why you have 55. Same lang ni siya sa n equal to 1 plus. Coach, hindi sa equation, Bob. Log.
Do ka laba na siya bimis nga ratio sang log. Do ka amo na iya itsura. Do ka same lang na siya mis nga pagkuha sang n.
This part, it is solving n here, you mean?
Oo, miss.
Oh, you just this one, this entire expression you transfer here on the left. This is 3 times 55 divided by 0.1. That would be 1,650. This minus 1 that you have transferred here, it should be added here. So that's 1,651. And then the rest is ln. You intend to determine a variable in the exponent of a number, so you take ln of both sides. Is that what you mean?
I-try ko na ako ng derive, miss. If same silang na equation sa nakita ko sa libro.
Oh,
Thank you, miss.
wait lang. Same na equation. This one, you're referring to this?
Daw amon ang tsura ya, miss. Pero more siya sa ratio ni x kag dy
Ah,
ang iya ginagamit.
so you can check. Pwede. You check with you check with the one provided by Jen Puplis if it's still the same. Okay, it will give you the same answer. You can check. Okay, I'll go back to the Jamboard then. Okay, so we have this. We go to letter B. No more question here. Okay, I'll go to B. So this is our final answer already for A. For your B, you must recall that you're given this data here. And as mentioned, this one could either be X or Y for a particular thickener. And this one refers to the capital W, amount of solution removed. So kilogram solution per kilogram pigment that goes with it. Now, with this relationship that is given, there's a need for you to find the linear relationship or the linear equation that will best represent this data. So I will show to you the equation that I placed on Excel for that particular, for the two set of data, and I will share it with you. So if you're going to use the two data, this will be the linear relationship that you'll be getting. Okay? So this is your X. And this is your W. And if plotted, it would be this line, straight line, since your R squared is equal to 1. And you have this equation. Y is equal to 0.2x plus 0.3. So we can change the Y to W, and we can change the X. We can have the X as X. Because, yes, W for the Y and X, still capital X for the X that we have in here. We need this particular linear relationship in determining the number of thickeners, which we will determine this time doing material balance per thickener. So we'll do material balance first overall, then we'll do material balance on each of the thickeners. Pabalik siya, and we'll do comparison. Okay, so that's the equation telling you the relationship of W and X. So I will close this now, and I'll go back to the Jamboard. So for our B, this is our equation. Of W in terms of X. So this is our second equation. Okay. Then from this particular equation, we need to determine the corresponding solute content based on the solution and its concentration. So we can have this generic formula of the amount of solute present in the thickened, the amount of solute present in your slurry leaving a particular thickener based on its concentration and its solution, the amount of solution that it has. So W sub n times capital X sub n. We'll have this as our equation 3. If we will substitute, our equation 2, substitute equation 2, wait class, 0.3 x sub n. Okay, if we will substitute equation 2 to 3. Okay, I did not label this in my notes. So if you substitute equation 2 to 3, this is what you'll have. Equation T will be now S sub n equal to, you copy all of this, and X sub n, and this is your entire omega, no, not omega, but capital omega sub n multiplied to X sub n. So this should give you 0.3 X sub n plus 0.2 X sub n squared. So that would be now our working equation of determining the solute content for a particular slurry leaving a thickener. So we can have this as equation 4. Okay? Please do take note of this. The equations. Anyway, the 2 was substituted to the third to give you this 1. Now, we can do now overall material balance. So, for 1 unit of titanium oxide process, if I will lump all the thickeners from thickener 1 to thickener n in just one thickener, so this is that particular thickener, and I will write here OMB. This is how it will look like. Okay. Now, I lump all the thickeners into just one, into this one thickener. You have this as your wash solvent, your wash water. If you notice, originally, this is 200 kilograms per second. Now, I only wrote here 2 because I am considering here a unit of titanium oxide process only. And remember, the original amount of titanium dioxide present is 100 kilograms per second. So in this case, then we have only for the 200 kilograms per second wash water used, I only place here 2. For this wash water, it doesn't contain any solute. So as such, the concentration is 0 for both. So 0, 0. This is how we represent the solute content, the amount of the final wash water, and its concentration here generally. We don't know them yet. For the feed, your feed contains 0.55 kilogram of salt. So our solute is the salt. So this S are solute. So the salt is 0.55 kilogram per kilogram of pigment. So that is why I place here only 1 unit of titanium dioxide process, because this is based only on 1 kilo of titanium dioxide. So it has 0.55 kilograms of the salt. So you have here 0.55 kilograms per second. Now in here, where is this 0.1 divided by 100 coming from? So it came from the table that we did. So the table that we did for the wash solid, the final wash solid, this is the amount of salt that it contains. The salt of the slurry from the end thickener. But this is for 100 kilogram per second of titanium dioxide process. And since in this overall material balance, this is for 100 kilograms per second of titanium dioxide. So we divided this 0.1 to 100. So it's now 0.001 kilogram per second. Now, for this capital W with the subscript 0, this refers to the solution. So we have a 1 kilogram solution of contaminant that comprises of the salt, which is the solute, 0.55 and 0.45, of course, water. So it's still 1 kilogram per second for the solution fed to the system of thickeners. Then the solution on the last thickener will be 0.3004. Now, question is, how did we get this W sub n, which is 0.3004? We have this equation here, equation 2, which is 0.3 plus 0.2, 0.3 plus 0.2 x sub n. This is your equation 2. So we solve your W sub n from there. So we'll have 0.3 plus 0.2. The x sub n, remember x, concentration, the concentration of the, in this case, your x sub n and your y sub n are equal, right? We have the assumption that these solutions are the same. So the x sub n in your underflow actually, based on the table that we have, has this amount. So you have 0.1 salt, and this is 50 water. So if you're going to get the concentration of the solution, will be 0.1 salt divided by salt and water. 0.1 salt plus 50 kilograms water. Now, if you're wondering why are we using this concentration of the underflow, in this case, because in the first place we're using, we want the concentration of the overflow. It's the X. It's because class anyway, the two are just the same. Equal lang man sila nga duwa. So I'll get the concentration of our solution here on the underflow because I have the information for that. So we have here, oh, sorry. So you will have here 0.1 over 0.1 plus 50. That should give you this answer. That is written here on the total amount of solution leaving the end thickener. So your answer here is 0.3004 kilograms per second. Again, your X sub n is based on Y sub n here from our table. Salt divided by salt plus water. Okay. So now we have our W sub n. Now we go to our sorry. We have our W sub n. Now we go to our Y sub n. That would be your S sub n over your W sub n. Your S sub n in this case is 0.001. Where is that coming from? Is here. Okay, the 0.001 divided by the W sub n we got in here. This one. The solution. So you will have 0.00, 0.3, 0.3004. Di ni siya naghalin, dire ah. This is the total solution leaving your end thickener. So the solute that it contains over the total solution will be 0.003329. Okay? We will continue with X sub 1. Determining X sub 1 is the solute in overflow of thickener 1. And this will be the basis of how we do reverse material balance to get to the number of thickeners that we need in this case. And we have here solution in overflow of thickener 1. Now, if we do material balance for this, the solute in the overflow of thickener 1 is equal to, based on our representations, still here on our overall material balance, this one, that would be your L sub n plus 1 solute in the wash liquor or liquid plus solute in the feed minus solute in the last thickener. Now, for the solution, you have omega sub n plus 1 plus solution in the feed minus solution in the last thickener. Now, you'll be able, here, if you substitute the values, you will have no solute in the wash water. You have SO to be 0.55. You have here 0.001. These are all taken from this one, from this illustration that we did. Lumping all the thickeners into one thickener. And then we have 2 in here plus, oh, sorry. Minus 1.0 minus, oh, sakto, it's plus, minus 0.3004. You will have an X1 value which is equal to 0.203. This would be the solution of the concentrated wash liquor that should leave your thickener number 1. The same concentration of the solution that goes with the slurry of that same thickener. So your X1 and Y1 are actually to be equal. So this is your X1 now. the next thing that we do is we should have a generic equation that will determine the concentration of the overflow. The concentration of the overflow, whatever it is coming from or wherever it is coming from whatever thickener it came from. So we will still have this guide. Solute in wash water to T sub n. This is the solute concentration of the wash water that was fed to a particular thickener. Now, this is n plus 1, and you notice this is n. We know that n plus 1 is coming from the stage after stage n. So that is why we have here solute in wash water to thickener n, because the wash water that is fed to thickener n came from the thickener which is labeled generally as n plus 1. So that is why you have here n as the subscript. I hope you get this one. This is the concentration generally of any wash water that enters a particular thickener labeled as n. You have here T sub n, and this is now n plus 1 here in the subscript because it came from thickener n plus 1. Now, the denominator of this is, of course, still solution in overflow from Tn. The solution in the overflow from Tn, and this is the solute in the wash water to Tn. Okay, that is your x sub n plus 1. In here, we can write the general mass balance to be L sub n plus 1 plus S sub I, the solute content of particular thickener I, minus S sub n. Here you have omega sub n plus 1. You have here W sub I minus W sub n. We can supply the information that we know already from this particular formula to this particular formula rather. So we have 0 plus S sub I minus 0.001. Now in here we have 2 plus W sub I minus 0.3004. Now simplifying further, you will have S sub I minus 0.001 divided by, I did not anymore subtract it, so that would be 2 minus 0.3004. Okay, you have 1.6999 minus, or rather plus, W sub I. This is your X sub n plus 1. So this equation will help us solve for a particular concentration. A particular concentration of the solution that is entering a particular thickener N. Because this one now is the concentration of the thickener N plus 1, the thickener after thickener N. Okay? I hope I am able to make you understand that one. A general equation that will help us solve the concentration of the wash water that's entering a particular thickener N. Now, we will need to do another material balance, this time based on that on thickener number 2. But before that, we need to do, para makita niyo si I, what particular I is that? This is your thickener I, and this is your thickener N. I is before N. So this is S sub I minus 1. This is S sub I, and this is S sub N. You have here capital WN, capital WI, and you can have here, in here that's already your omega N plus 1, the small w, and we have here your omega I plus 1. I plus 1 in the sense that this one came from the ith stage plus 1. So if this is 2, this came from 3. W3 na ni siya bilang. And you have here your W sub I. So you have the representations in here. If you get, because I already have the x sub 1 equation in here. So if you're going to substitute, wait class. That would be now equation 4. This would be our equation 4. So from 3 or from 4, we'll have your x sub n plus 1 equal to negative 0.001 plus s sub I. You have 1.6999 plus w sub I. Your I is actually your n minus 1. Okay, because if this is 10, this must be 9, where I is equal to n minus 1. Now, if we solve for omega 1 in here, since we're doing material balance, we're going to do material balance on 2. Thickener 2 will have negative or 0.3 plus 0.2 x sub 1. And this will be 0.3 plus 0.2 times the x sub 1 that we have, which is 0.203. This 0.203 class is this x sub 1 here, the one that we have solved in here. So we already substituted it in there, and we have 0.3406 for our solution, leaving thickener 1 in that case. Now, if we'll find S sub 1, the solute, that would be the solution times X sub 1. And in this case, that would be the answer that we have here, which is 0.3406 times the X sub 1 that we originally determined to be 0.203. And actually, we have this particular equation, which has the, if you recall, the x squared here. You can also use this one. This one. S sub n is equal to 0.3 x sub n plus 0.2 x sub n squared. You can also go directly to that. Actually, this is actually, sorry ha, di ko na ma-keep track ang equation. So this would be now your equation 5. So you have this S sub 1 to be equal to 0.0691. This is the solute, leaving your thickener 1. So from here, you can solve for x sub 2 now based on the equation that we have. Ini nga equation 5 that I labeled originally as equation 4. So you have x sub 2 is equal to negative point plus, this is already s sub 1. Your s sub I, your I is n minus 1. And since your n is 2, so this would be 1. And you have 1.6999 plus omega, rather capital W1. Rest is substitution again. So 0.001 minus, rather plus 0.0691, this one here, divided by 1.699 plus the omega 1, this one, which is 0.3406. So you're going to get an x2 value, which is 0.03337. Now, remember, I'd like to put an arrow on what we're doing. We started with determining the concentrations of the overflow. So that's overflow 1. This is overflow 2. Okay? That's 0.03337. We will continue solving. Just let me borrow around 5 minutes, ha? We'll just finish this one. So your S2 will be your capital W2, X2. And this is equal to 0.3 plus 0.2. Your X2 as solved in the previous page here, this one, 0.03337. This you will multiply by 0.0337. Another 3. Let's check. Okay, 3 3s. So you will have an S2 value which is equal to 0.010234. Now that's for the S2. After you have done the S2, you determine the concentration, leaving thickener 3 based on the solute content that thickener 2 has. So that would be equal to, you know that you need to solve for the solute content of the previous thickener because the equation that we had class generally is based on that. You see this? Si minus 0.001 over 1.6999 plus Wi. And this I is actually your n minus 1. So that is why there's a need for you to determine S2 for you to know S3 and so on and so forth. S1 for you to know X2. So your X3 is negative 0.001 plus S2 over 1.6999 plus W2. And this would give you, after substitution, so negative 0.01 plus 0.010234 for S2, 1.6999 plus a small double, capital W of W2 where's our W2? This entire thing, class, if we do this entire thing, the W2, I did not place it anymore there, is 0.30092. Wala ko na siya gin-solve, indiretso ko na lang. Ini, 0.3 plus 0.2 times 0.0337. So you will have an X3 value of 0.30092. So your X3 would be 0.00460188. It would be best, I'll go later, go back to the solution for you to have ease in following this through. You take a screenshot so you will have continuity in studying. So when you're done with X3, you can now solve for S3, which you need in X4. So S3 is equal to capital W3X3. So your W3 is 0.30092 here. Oh, wait lang. Your W2 here, because you need to take a screenshot of this later, is 0.30. Based on this one class, because you will later on see that it's not the value that I have originally written, 0.30667. Because your W3 is the one that is 0.30092. You multiply it to X3, which is 0.00460188. You will have an S3 value of 0.00138847. S3. So we continue with the last X4. I'll tell you later why you need to stop already. You will have equal to negative 0.001 plus, of course, this is S3 over 1.6999 plus capital W3. You're going to get an answer here if you substitute negative 0.001 plus 0.00138847. We divide by 1.6999 plus omega 3, which is 0.30092. You'll get an X4 value of 0.001923. Now, this process of you getting the X will only end. So you first determined, initially we determined X1, which is 0.203. Then we went to X, we determined the formula that will solve for the rest of the X. So we'll have now, we had now X2, then we had X3, and this is the last one, the X4. When will you end solving for this excess, the concentration of the overflow? You will end X when its value is less than X sub n. Now, where is this X sub n? Okay, where is that X sub n? You remember this one? We have 0.001 divided by 0.304. If you're going to solve for the Xn, this is not 2 class, this is n. Xn is equal to Sn over capital Wn. Your answer here, you just go back, 0.001 divided by 0.3004. Which will give you an answer which is 0.001 divided by 0.3004. Will give you an answer which is 0.00333. 2. So you will only stop solving for X when its value is less than 0.00332, meaning you have achieved already this particular amount of solute in the slurry. So meaning it's already admissible because the solute content in your slurry, in your concentrated wash liquid is already acceptable. So you have 0.003332. Now, in this case, our X sub 4 is this one. 0.000192 This is less than 0.003332. We did not stop at 3 because it's still 0.004. We did not stop at 2 because it's 0.03. We need to stop when our concentration is lesser than x sub n, which is 0.003332. Ang nabilin sa inyo slurry, gamay-gamay na lang kayo nga solid. So, if this one is the concentration that remains in the slurry, then this is already okay. This is already acceptable. Okay, 0.001923 is already less than 0.003332. So we say, therefore, your N should be more or less equal to 4 because you're getting a concentration here which is lesser. Actually, class, if you look at this in our computation, iyan siya sang overflow. Ang iya sa overflow, amo man na ang concentration sang underflow. So, ang ginatanaw ta, mauntat lang ta washing kung ang solute contents ang aton underflow nga solution gamay na or ma-conform sa final solute content nga gusto ta based on the overall material balance. Because we got, I'll go to the this one, we got this Sn and Wn, which will lead to us to the Y sub n, also equal to X sub n from the overall material balance. So, dirita gidyaging kwa ang guide ta nga kung saan o ta mauntat solve sang X from the overall material balance. So, you take your Y sub n here, also equal to your X sub n from your solute, and for your solution values or amounts in the slurry leaving your nth thickener. Okay? So that's it. So malawig siya kung ga-vary ang aton nga removal of the solution in the slurry based on the concentration of that same solution. Because you have to do material balance on each of your thickeners. This is the case. You have any question? 3 minutes past 12:30. If you want to take a screenshot of the slides, I will let you. So you will have continuity in studying. I'll give you some time to take pictures. Right now. Pwede nyo i-review ang recording, but you can also follow through. Oh, sorry. That's the kinetics already. Follow through here. Okay. Here, class. So this is Lawigid Alisa. Dutay ang discussion sa leaching, pero I will understand if you say sometimes do madula ka na kung di ano nang imo gina-balanse. But it's really material balance here. Unless otherwise, you'll do the graphical. If you have time, you can check on Genco, please. You'll do the graphical approach of Genco, please. But you cannot make use of that because you hindi ka man magsagi drawing linya sa board exam. So, mabalanse ka gidya. Yeah, that's correct. Ang iya lang advantage sinika kay way ka sang balik-balik lain niya sang iteration nga mabalik-balik ka solve gabalik ka sa puno bala diri way ka gabalik kasi sige-sige ka lang mauntat ka lang kung ma-reach mo na to ang final concentration nga na-determine mo na sa overall material balance. Pero ini siya nga scenario is when gani ang the amount of the solution that is to be removed is dependent on the concentration of that solution. Pero kung letter A lang man, nga wala siya ga-vary, then dali man lang siya solvon. Galing amo ni, kinanla niya ang understanding mo sang problem sang material balances. Mayo, na understanding, the bottom line here is what goes to what amount goes to this, mga amo na siya. kay puro lang gid sa tanan balances ang material. So anyway, if you'd like to take a screenshot, you can take the screenshot of this now. 1, 2, 3. Page 2. 1, 2, 3. Page 3. 1, 2, 3. 4. 5. You can do away with this and this if you have this one already. If you know W and X, diretso ka na di pwede. 7. So always start with the overall material balance. It will guide you with the X sub N or the Y sub N. 8. You always start with the first thickener, concentration. 9. An equation that will lead you to solving the rest of the concentrations in the overflow. 10. Eleven. 12. 13. 14. Okay, we can have now your lunch break.